Hey guys, in this video we are going to see about linear regression and the maths behind linear regression as a part of the basics of machine learning series, and this is the second video in it. So what we will be discussing in this video is the mathematical formulation of the linear regression and the closed form solution for the linear regression. What is the closed form solution? We will see it in the video. So what's the price of the house? This is the same question we asked in the first video, but we took only the area of the house. We didn't take into account the age of the house and number of bedrooms and area of the pool. Assume all houses have a pool. We didn't take all these into consideration, but in a real life situation we need to take all these into consideration. So how do we do it? The same way we did with the first one. Assume a linear relation between all these parameters and take as w0 plus w1 x1 plus w2 x2 plus w3 x3 plus w4 x4. And what are w0? W0 is the intercept or the bias. When all x1, x2, x3, x4 are 0, y need not be 0, right? In any general case. So we have a bias term. X1 is the house area, x2 is number of bedrooms, x3 is age, and x4 is pool area. And w0, w1, w2, w3, w4 are the weights. These are very important. Our aim is to find the weights. What we just saw is multiple linear regression and not a simple linear regression, because we had more than one parameter as our input. The features of the multiple linear regression is multidimensional because it has more than one parameters, and the labels is just a single scalar. Our price is our label. Our aim is to predict the price and it's just a single number. Our loss function we are going to use is the mean squared loss function, as we saw in the first video. And when talking about the solution, closed form solution exists and iterative solution also exists in the gradient descent. In this video we will be focusing only on the closed form solution. In the general case, let us assume there is d minus 1 features and x1, x2 until xd minus 1 are the features, and I is a point in the data set. So this is a vector from the data set, and we need to find the function f, which is a linear function to which gives us the target value yi. The function f of xi is w0 plus w1 x1 plus w2 x2 and so on until wd minus 1 xd minus 1, which is yi hat. So this is the predicted value and this is the target value. Our aim is to bring these two as close to each other. And what is the measure of closeness? The measure of closeness is this loss function 1 by n sigma I equal to 1 to n f of xi minus yi the whole square, where f of xi is the predicted value and yi is the target value. So this f of xi is nothing but w0 plus w1 x1 plus w2 x2 and so on, and wd minus 1 xd minus 1. So it can be written as a product of two matrices as w0 w1 until wd minus 1 into 1 xi1 xi2 until xid minus 1, which is nothing but w transpose xi. So this is w transpose into xi. So let's get a complete view of the question. So we have data set features, which is x1, x2, x3, xn. So this is the data set, and each x has a dimension of d, right? There are d minus 1 parameters and 1 for the bias, and the data set labels belong to R because they are a scalar. They are simple scalar, that is nothing but the price of the house. So our function f of x is w transpose x, and our aim is to minimize 1 by n sigma I equal to 1 to n f of xi minus yi the whole square. This is our aim. Let's solve for w. So solving linear equations is simple. Let's solve for w, assuming there exists the perfect w for the given y. And how many variables do we have? We have w as the only variable, which it has with the d dimension. So there we have d unknowns. How many equations? 1, 2, 3 until n. So we have n equations, d unknowns. In general case, the number of parameters would be usually less, like 4 parameters. We have 4 parameters for the houses, but the data set usually is very large. We have like 1000 houses, 20,000 houses. So usually d is very small than n, or rather n is very greater than d. So this problem can be written in the matrix form as x1 transpose, x2 transpose, x3 transpose, xn transpose as the rows of a matrix times w, which is equal to y1, y2, y3, yn, and this we call this as capital X and this as y. So what is the dimension of this matrix? X1 has d elements and we have n rows. So this is an n cross d matrix. So we have to solve the equation capital X w is y, and immediately you may think, why don't you take w equal to x inverse y? Can you do it? The answer is no, you can't do it. We are stuck in this moment because x is not a square matrix. First of all, in general, yeah, when n is d, x is a square matrix, but in general x is not a square matrix. You can't take an inverse if x is not square. You don't have a perfect solution all the time. Now we need to get a solution. How do you do it? Instead, minimize the error and get an approximate solution. So we now change our aim. Before, our aim was to find the w for the target values, but now we saw that it's not possible. Now you go to the minimum possible error between our predicted value and the real value. So the vector of prediction is xw and the vector of targets is w, and mean square error is 1 by n this whole square. We need to minimize this. This can be written as xwy the whole transpose times xw minus y, as L2 norm of x is x transpose x. So minimizing the error, we take the differentiation with respect to w and equate it to 0. That's what we know from calculus, and this symbol is delta, and with respect to w, that is gradient with respect to w, that's nothing but differentiating with respect to w and equating it to 0. So this is nothing but xw minus y the whole transpose times xwy. Let's take the transpose inward, w transpose x transpose minus y transpose. Let us open the two brackets. You get w transpose times x transpose x times w minus 2 w transpose x transpose y plus y transpose y. So this is the final equation, and this is dependent on y transpose w, and this is dependent on w transpose, but this is independent of w. So differentiation of this becomes 0, and this becomes 2 times x transpose y, because differentiation of x transpose y with respect to x is y. If you don't know matrix calculus, just comment down below, we'll make a new video. So differentiation with respect to w transpose x w is nothing but 2 times x transpose x w. So now what we have got? What we have got is 2 times x transpose x w minus x transpose y is 0. That's nothing but x transpose x w is equal to x transpose y. Now again ask this question. As we already saw, x is an n cross d matrix. X transpose x is a square matrix of dimension d cross d. Can we take inverse now? Yes, we can indeed take the inverse now, because it's a square matrix and usually all the parameters are independent of each other. You don't have number of rooms twice in your data set, right? We have it only once. All the parameters usually be very independent of each other. Usually, hence we will have an inverse in a general case. So our solution w is x transpose x whole inverse x transpose y. So what you need to remember is the closed form solution for the linear regression case is x transpose x whole inverse x transpose y, and we have done it at last. So this is the closed form solution we needed, and we indeed did get it. So yeah, hashtag least squares. So that's all for this video. Thank you.